Hello everyone and welcome to General Chemistry 2, lecture number 10. This is the third and final lecture on kinetics, and here we're going to learn about integrated rate laws. This is OpenStax section 17.4. So first, a brief review on rate laws from lecture 8. So rate laws relate the reaction rate to the change in the concentration of the reactants over time. So for a reaction A plus B forming C, where the capital letters here represent the identity of some compound, the reactants and the products, and then the lowercase letters here represent the coefficients. So we learned about these right here. So these are referred to as rate expressions, and it's a way to relate the change in concentration over time to the rate of the reaction. We also learned then about rate laws, which really relate the concentrations themselves to the rate of the reaction, where X and Y are the reaction orders for the reactants A and B, respectively. K here is the rate constant. Remember, delta meaning change. Here we have these negative signs because A and B are both reactants, again, as covered in lecture number 8. As we learned, the reaction orders indicate to what extent the reaction rate depends on the concentration of each reactant. Continuing on, if the reaction rate varies proportionally or linearly with the concentration of only one reactant, the reaction is first order. So again, a review of what these reaction orders mean. If the reaction rate varies exponentially, or essentially squared, with the concentration of one reactant, or is dependent on the concentration of both reactants, the reaction is second order. So here we're talking about overall reaction order. So this is saying, this first point here, that if it varies proportionally with only one reactant, so suppose that A is first order and B is 0th order, we would say then that the reaction is overall first order. So the overall order of the reaction can be found by essentially summing the reaction order of the reactants if there are multiple reactants. Then the second point is saying that if the reaction rate varies exponentially with the concentration of one or is dependent on the concentration of both. So this means that, for example, suppose A was second order and B was 0th order, that would satisfy this first statement here, where it varies exponentially with the concentration of one reactant. If A is second order and B is 0, the reaction rate is overall second order. Or if both of our reactants here were first order, if both A and B were first order, the overall reaction order, again, would be the sum of those two, which is what this second point is describing, is dependent on the concentration of both reactants. The reaction is second order. If the reaction rate varies independently of the concentration of any reactants, even if you have multiple reactants, if they were both 0 order, the reaction is overall 0th order. All right, now on to integrated rate laws. We can also write rate laws in a different form that allows us to track the concentration of the reactants over time. This form of the rate law is called the integrated rate law. So here we're going to just look at a simple case. We're just going to be dealing with one reactant here to make the math easier. So for a reaction which is first order in reactant A, we can say that rate reaction equals negative delta concentration of A over A times delta T. And here, remember, the little a would be the coefficient on A in the balanced chemical equation. Or for the rate law, we can say rate reaction equals K times A. And since A is first order, again, that exponent, that there's an unwritten 1 right here. The integrated rate law can be written in one of two forms. You may see it written like this. This is the original form that is derived based on essentially integrating under the area under the curve, if you were to plot this as a function, which is why we call it an integrated rate law. But more commonly, you will see this form of the equation, because here we see that we have an exponential, and exponentials are a little challenging to work with, especially if we've got some variables up in that exponent. So if we take the natural log of both sides, you get this form of the integrated rate law. Natural log AT equals negative KT plus natural log of A0. AT here is the concentration of reactant A at some time t. K is the rate constant, and natural log A is 0. The 0 here means initial, so this is the initial concentration of reactant A. So for a first order reaction, if you were to plot the concentration of A versus time, you get something that looks a little bit like this. And this equation is essentially derived from integrating the area under this curve. So this is something that if you've taken Calc 1, you understand what this is. If you have not taken Calc 1 yet, this isn't going to make complete sense to you. But again, the basic idea here is this equation comes from the area under this curve. There's something called integration in calculus where we can basically find a function that defines the area under a curve and has that area changes as here the x value, or which would be t here, changes or increases or decreases. But you don't need to know how to derive that equation for this class. The important thing to know is this version of the equation, and we especially like this form because it gives a straight line when graphed. So notice then for a first order reaction, when we plot the natural log of concentration versus time, we get a nice straight linear line with a negative slope. We really like this form, not only because it gives a straight line when graphed, but also because it gives a straight line, we can note the similarity of this equation to y equals mx plus b, where natural log at is our y value, little t for time here is our x value, natural log a0 is our y-intercept, and then negative k is going to be the slope of this line. So by plotting this data, we can determine the rate constant for whatever reactant or whatever reaction this is. A reaction is second order if the overall reaction order is 2. There are a few different ways this can occur. We could have one of our reactants being second order, one of our other reactant being second order, or both our reactants being first order. Again, for the purposes of making the math easier, we're going to only consider ourselves with the first case, technically the first two cases, because the first two cases represent the same thing, second order with one reactant, but we're going to stick with using the variable A to be consistent here. The math gets a bit more complicated if you have two reactants that are both first order to give an overall second order reaction. So working with this case here, the integrated rate law for a second order reaction is this: 1 over AT equals KT plus 1 over A0. So you can see that it is a fairly similar equation, right? The first order one had natural log AT here and natural log A0 here. Instead, we have the inverse of those concentrations, and then our K value is positive instead of being negative like it was with the first order. But note again that this equation mimics the form of y equals mx plus b. So plotting 1 over AT versus little t for time will give a straight line with slope k. All right, and finally, onto the zero order reactions. A reaction is zeroth order if the rate of reaction is completely independent of the concentrations of any of the reactants. So if we were to write this out, sticking with that same generic chemical equation of having two reactants A and B, if the overall reaction is zeroth order, then A and B must also be zero order. So anything raised to the 0 power is 1. So this rate law would simplify to simply rate equals K. The rate of the reaction is equal to the rate constant for that reaction. The integrated rate law for a zero order reaction is this: AT equals negative KT plus A0. Again, pretty similar to those first two. It's got the negative slope like first order does, but now it's just concentration for your y value here and for what is essentially your y-intercept value here. All right, let's do a little bit of practice with first order reactions. The reaction 2A to B is first order in A with a rate constant of K equals 2.8 times 10 to the negative second inverse seconds at 80 degrees Celsius. How long will it take for the concentration of A to decrease from 0.88 molar to 0.14 molar? All right, so right away, I notice that the problem says, or in the wording of the problem, it says it's first order. So oh, sorry about that. I thought I had my work on the slides here. Okay, sorry about that. I just took a brief moment to pause the video and add the work in here since this wouldn't be much help if I didn't show the steps I did. Okay, so back to this problem. Again, we are looking to determine how long it will take for the concentration of reactant A to decrease from 0.88 molar to 0.14 molar. Since this reaction is first order, I'm going to use this version of the integrated rate law. I'm going to start then by identifying what variables I've been given and what I'm being asked to solve for. So I notice that I've been given my K value. I've also been given two concentrations. And then the problem says how long will it take, which obviously means we're solving for T. We're solving for the time. So if I take this equation and rearrange it to solve for T, I'll take this and subtract it from the right to the left, and then I'll divide both sides by negative K, and I get this equation where T equals natural log AT minus natural log A0 divided by negative K. I can go ahead and plug my variables in. So here, see how it says to decrease from 0.88 molar. This implies then that the 0.88 molar is the natural log, or is the A0. So 0.88 molar goes in for A0, and 0.14 molar goes in for AT. And then here is the rate constant K plugged in down below, and that negative sign comes from the integrated rate law. If you plug this in and solve, you should get somewhere around 66. So it would take about 66 seconds for A to decrease from 0.88 molar to 0.14 molar. All right, one more example problem. This one states, when heated to 300 degrees Celsius, nitrogen dioxide decomposes to nitric oxide and oxygen in a second order reaction. 2NO2 forms 2NO plus O2. The problem states the rate constant for this reaction is K equals 0.54 M-1 S-1. If a flask that initially contains 0.056 molar of NO2 is heated at 300 degrees Celsius, what will the concentration of NO2 be after 1 hour? All right, so I'm working with a second order reaction. So I'm using this equation, 1 over AT equals KT plus 1 over A0. Now note that I'm being asked to solve for concentration. It says, what will the concentration be after 1 hour? So actually AT here is the unknown, so I don't really need to rearrange this equation at all. You could invert this now if you prefer to, but I prefer to work with it as is and then invert at the end to get the AT out of the denominator here. So I'm just going to go ahead and plug in my values. K is 0.54 M-1 S-1, so that gets plugged in here. T is the time. Now be careful here. Notice in the problem it says after 1 hour, so you may be tempted to just immediately put a 1 in here, but watch your units. The rate constant K has units of inverse seconds, which means whatever I plug in for the time T also needs to be in units of seconds. So 1 hour is 3,600 seconds. So 3,600 seconds goes in for T. And then here, the initial concentration goes in for A0, 0.056 molar. If I multiply this out and solve, this times this plus this value gives me around 1961.86. So I get 1 over AT equals 1961.86 M-1 molar to the -1 power is the unit. And then if I just invert both sides, so I take 1 over this value, I get AT equals 5.1 times 10 to the -4th molar. And this is the correct answer for this problem. Okay, so now let's look at linear forms of the integrated rate laws and how we can use them. So we can use the linear form, the form that we've been using the last couple slides, to determine the reaction order if we have corresponding plots of experimental data. After collecting a set of concentration data at several time points, we can create 3 plots. We can create a plot of concentration versus time, natural log of concentration versus time, and the inverse of concentration versus time. Because if we think about the integrated rate laws we were just looking at, 0 order is concentration versus time, first order was natural log of concentration versus time, and second order was the inverse of concentration versus time. So if we plot these three data sets for a set of concentration versus time data, we can then analyze, and whichever plot shows a linear relationship is going to give us a pretty big clue, if not essentially outright tell us, the overall reaction order. So let's look at an example of this. The set of graphs below were all created from the same reaction data. The plot of natural log versus concentration is linear, which indicates that the reaction is therefore first order. So if you're given, you may be given a problem like this, whether it be on a homework, quiz, exam, etc. For my classes, that's homework or exam. And you want to look at the data, look at the three plots. Whichever plot has the best linear fit, that's going to tell you the reaction is for first, whether it's zero, first, or second order. So take a close look. Oftentimes you can just tell immediately just from how it looks visually. So if I look at concentration versus time, this fit right here, this black line, it's a pretty good fit, but that blue data still has a little bit of a curve to it. And if I look at the second order data, the inverse of concentration versus time, again, the linear fit here is pretty good, but that blue data still has a little bit of a curve. Doesn't appear to be quite linear. Whereas here, when I look at natural log of concentration versus time, those blue data points line up almost perfectly, and they form that nice straight linear line that we are looking for. If the data also includes r squared values, so remember that r squared is called the coefficient of determination. It tells you how good of a fit the data is, and the closer r squared is to 1, the better the fit is. So you can often just look for the data that has the highest, or I should say the r squared value closest to 1, which also goes to this plot right here. And again, since this is the natural log concentration versus time, this tells us the reaction is first order. All right. Now, additionally, we can ask our graphing program to display the equation of the linear regression, basically the best fit line here. That's y equals negative 0.0175x minus 4.4228. Given the pattern below, we see that the negative slope of the linear equation gives us the rate constant k. So we can determine some things right away. We could determine the initial concentration. So if you set natural log a0 equal to the y-intercept, so if you set this equal to this and then solved for a by basically raising both sides by power of e, you could solve for the initial concentration. And what's probably a little more important is the rate constant. We can see from this version of the equation that the slope of the line is negative k, and so since the slope of the line is negative 0.0175, we could then say that the rate constant k equals positive 0.0175, right? See, we get these negatives right here, so k equals just this value, 0.0175. All right, let's have you try a practice problem. Here's a set of plots for a different reaction. First question, what's the reaction order? And second question, what is the rate constant k? So take a moment, pause the video, and see if you can answer these two questions. All right, first question, what's the reaction order? You should have come up with second. This reaction is second order because the inverse of concentration versus time has the best fit. Question number 2, what's the rate constant k? If we look at the second order integrated rate law here versus the equation derived from that fit, we can see then that the rate constant k simply just equals the slope of the line. So we could say then that k equals 0.0085. All right, next, onto the concept of half-life. Half-life is defined as the time it takes for the concentration of a reactant to decrease to half of what it was initially or previously, whatever you are looking for. So half-life, the time it takes for the concentration of a reactant to decrease to half of what it initially was. A reaction does not go to completion in two half-lives. Right? We can't add two half-lives together to get a, quote, whole life. So if we were to analyze this, after each half-life, the concentration of the reactant will be half of what it was before. So it's a pretty descriptive term here. So the reactant concentration after the first half-life will be 1/2 of what the initial concentration was. The reactant concentration after the second half-life will be half of that half, or 1/4, 1/4 of what the initial concentration was. If we went to a third half-life, we'd be down to 1/8, a fourth down to 1/16, and so on from there. For first order reactions only, the half-life is constant. We can use this to easily think about how the reaction concentration will change over time. Again, it's cut in half for each half-life that elapses. So for example, if you had a certain first order reaction with a half-life of 15 hours, this means that after 15 hours, half will have been consumed. After another 15, half of what remains will be gone, and so on from there. So if we assume that we start with 20 grams of this reactant, the question we're posing is, how many grams will be left after 4 half-lives? So let's say we're starting with 20 grams. After 15 hours go by, 1 half-life goes by. So we go from 20 grams to 10 grams. After an additional 15 hours, so now 30 total, we've gone through 2 half-lives, so from 10 now down to 5. After another 15, so 45 hours total, 3 half-lives, we would go down from 5 to 2.5. And then after an additional 15, for that 60 hours, we'd be down to 1.25 grams. So see, we divide by half each time. 20 to 10 to 5 to 2.5 to 1.25. And so the answer here would be 1.25 grams remain after 4 half-lives. So again, this is the overly simplistic half-life explanation, and this applies to first order reactions. 0 and second order are a little more complicated. All right, so in thinking about half-lives in this way, we have only considered the simplest case, the first order reaction, where the half-life is constant. Again, this is only the case for first order reactions. So we see from the graph here, we just have concentration versus time plotted. So we start at 0.20, and it takes approximately 7 seconds. So if I look at my graph here, to go from 0.20 to 0.10, which would be exactly half, we see that that's 7 seconds. It takes 7 seconds for half of this concentration, or half of this reactant's concentration to degrade, to disappear or be consumed. Now we're at 0.10, so if we follow along, half of that would be 0.50. So from 0.10 to 0.50, I can see it goes from time 7 down to time 14. So again, another 7 seconds. And then you could trace that for a third half-life, for a fourth, and so on. So it takes 7 seconds in this hypothetical example for half of the reactant to disappear. And so this is constant for a first order reaction. For a zero order reaction, the half-life actually gets shorter as the reaction progresses. So if we look at concentration versus time, noting here that it's a straight line, which makes sense given what we just learned about with the graphs of the integrated, or the graphing the data and comparing to the integrated rate laws. So a zeroth order reaction from 0.20 to 0.10, we see that it takes approximately 30-ish seconds, maybe 33 seconds or so. And then to go from 0.10 to 0.50, now this is only taking about 17 seconds. And then 0.50 to 0.250, now it's taking, close to 8 seconds. So you can see that the half-life is actually decreasing by half. And eventually, this reaction would rapidly decrease to a concentration of 0. So with a zero order reaction, the concentration will actually go down to 0 because the reaction rate is not dependent on the reactant concentration. So the half-life here actually decreases. The half-life is not constant for a zero order reaction like it is for a first order reaction. And finally, when we look at a second order reaction, the half-life of a second order reaction actually increases. It gets longer as the reaction progresses. In a second order reaction, the reaction rate is exponentially related to the concentration of reactants. So the reaction rate slows down significantly as the reactants are consumed. So if we look at this example, to go from 0.20 to 0.10, it takes about 50 seconds. And then from 0.10 to 0.05, it takes almost twice as long as that. It takes close to 100 seconds. Then from 0.05 to 0.25, now this takes almost 200 seconds. So here you can see the length of the half-life is actually decreasing. The length of the half-life is increasing with decreasing concentration. It's almost doubling. 50 seconds to 100 seconds to 200 seconds, we can expect it would continue to double in each subsequent half-life. So again, remember that half-lives are only constant for first-order reactions. Half-lives will decrease for zero-order reactions, and half-lives will increase for second-order reactions as concentration decreases. All right, now let's look at how we can relate half-life to reaction rate. Because of this, we typically use different formulas to allow us to relate half-life to the reaction rate and reaction order. First, let's look at our variable here. We're going to define t to the 1/2 as our half-life here. So t to the 1/2 is the time at which AT equals 1/2 A0. So when the concentration equals half of the initial concentration. So if we take these variables and insert them into the integrated rate law, so insert t to the 1/2 for t, and insert 1/2 A0 for AT, so I'm using the first order integrated rate law. If we solve for t to the 1/2, basically this term was subtracted from the right to the left side, and these variables, when this is subtracted over, this minus this actually simplifies to just natural log of 2, and then we can move k to the other side. And we get the expression t to the 1/2 equals natural log 2 over k. I know that I skipped a lot of algebraic steps here from step 2 to step 3. I am personally not going to expect you to be responsible for deriving this yourselves. You will be given this equation, but if you're curious how I got from here to here, take a moment and work it out on some paper. Remember your natural log algebra rules, and you should get this equation right here. So t to the 1/2 equals natural log 2 over k. This roughly equals t to the 1/2 equals 0.693 over k. So you may see both forms of these equations on a reference sheet. You may see both of these referenced or used. Basically, natural log 2 is roughly equal to 0.693. So again, you may see either version of this equation. Once again, we have used the integrated rate law and used these properties right here. T to the 1/2 is the t at which AT equals 1/2 A0 to derive the half-life for a first order reaction. If you want to give it a shot, you can derive the formulas for both second order and zero order reactions. So I am again showing that work here, just simplified. Whoop. Oh, sorry about that. Actually, sorry, my slides are not in the order I thought they were. So I am showing you the setup here for a zero order reaction and a second order reaction, where you plug in 1/2 A0 in for AT, and you plug t to the 1/2 or t 1/2 in the subscript for t, and I'm showing that here for second order reaction as well. I will show the completed versions of these formulas in just a moment. I thought I had them on this slide. Again, I would welcome you to go ahead and give this a shot to see if you've got the algebra skills down to solve for t to the 1/2. I will reference back and show you the completed formulas in just a moment. I want to real quick show an example of what one of these problems may look like. This question states, what is the half-life of N2O5 if it decomposes with a rate constant of k equals 5.7 times 10 to the negative 4th inverse seconds? So first question, how do we know what formula to use? Or more importantly, is there a way that we can determine whether the reaction is first order, second order, or zero order? And you should remember that yes, there is. As discussed in the previous lectures, it depends on the units. Remember that you can tell what order the reaction is based on the units on the rate constant. Here we see that our rate constant has units of inverse seconds, which means this reaction is first order. And so to solve this problem, you would use this equation. This is the half-life equation for a first order reaction. T1/2 equals natural log 2 over K. Since you are given K, all you need to do is take this and plug it in down below. And I believe you get an answer of somewhere around 1200 seconds for this problem. So first order is the easiest case in which you can just plug the rate constant in and solve for T1/2. All right, here is a summary of the kinetics of first order, second order, and zero order reactions. As mentioned, here are the half-life equations for zero and second order. So to review, with a zero order reaction, the rate law is simply rate equals K. The integrated rate law is AT equals negative KT plus A0, and the half-life equation is T1/2 equals A0 over 2K. First order is summarized here. We've talked about this. And second order is summarized here. The half-life equation is T1/2 equals 1 over K times A0. Reaction orders greater than 2 are virtually non-existent, and so we will not consider them here in our kinetics lecture. Okay, I'm going to briefly review a couple types of kinetic calculation problems that you may see. So this is summarizing everything we've covered in kinetics from lectures 8, 9, and this one, lecture 10. So you may be asked about average rate of reaction and relative rates. This comes from lecture 8. You may be given starting and ending concentrations of a single reactant or product over a span of time, and then you can solve for the average rate. So remember how to write your rate expressions. You may need to relate this to the rate of consumption or formation of a different reactant or product using their stoichiometric ratios. So remember that the relative rates here are directly related by the stoichiometric ratios from the balanced chemical equations. Remember also instantaneous rate. This again was from lecture number 8. So given a graph of concentration versus time, determine the rate of reaction at a specific point in time. You need to draw a tangent line to a curve. So again, want to note that I'm not going to ask you something like this on an exam. So me personally, I will not do this. It may come up in the homework, or if you're not from Wake Tech and you're just watching my videos because you like them, this may be something your professor asks you to do. Make sure you understand generally how to draw a tangent line and then determine the slope of that line. And finally, the big one from lecture number 8, method of initial rates. So from the second half of that lecture, when we learned about rate laws, given rate and concentration data for several trials, you will be asked to compare the trials to determine the reaction orders for the reactants, to write the rate law, and then find the rate constant K by plugging in some of that rate and concentration data. And continuing on, what we covered last lecture, Arrhenius equation problems. So remember that the rate constant K, is directly related to the temperature exponentially via the Arrhenius equation. So relating the rate constant K versus temperature T to determine the activation energy EA. So a plot of natural log versus the inverse of temperature will give a linear equation with the slope negative EA over R. So that 2-point format was used to find EA given temperature and rate constant values. So remember the two different forms of the equation, the linearized version of the equation, which you'll use if given a plot of natural log K versus 1 over T, and then we have the 2-point format, which you can use to find the activation energy given two sets of temperature and rate constant values. And then finally, from this lecture, using the integrated rate law, generally you will be given a set, you'll be given 3 different plots and be asked to determine the overall reaction order based on which plot is linear. It's 0 order if the graph of concentration versus time is linear. It's first order if the graph of natural log concentration versus time is linear. And finally, it is second order if the graph of the inverse of concentration over time is linear. You can determine the rate constant K from the slope. You can also determine the initial concentration based on the y-intercept. And then if reaction order is known, you can use appropriate formulas to solve for the rate constant, to solve for concentration, to solve for time, or you may be asked to solve for half-lives. All right, that's the end of this lecture. I have 2 additional practice problems here for you to try. So go ahead and pause the video, give these 2 problems a try. And here are the answers to those 2 questions. That concludes this lecture. Thank you for watching all the way through. I hope you enjoyed it and found it helpful. As always, please feel free to reach out to me if you have any questions. I'll see you in the next one. Have a great day.